So, good morning, everyone. Maybe I think we'll wait another couple of minutes, actually. Maybe 1 minute before we start. I see people are still dropping in. Right, so yeah, we are recording this, just to let you know. You're still very welcome to ask questions live, but you can also post them in the chat if you have things you want to bring up. I'll try to keep track of that. Okay, I think I'll start. So, yeah, good morning once again and welcome to this lecture in the course Advanced Machine Learning Using Neural Networks. My name is Mats Granath. I'm one of the lecturers for the course and I'm responsible for homework A, which is on graph neural networks. And that's what I'll aim to give an introduction to this morning. Yeah, we have a question here. We will record all the lectures. Yes, we will. That's the plan. Oh yes, and I have a few information points before I actually start with the lecture. So yeah, so one on the recordings, those will be posted on the Canvas page. So there will be links there, so you can find recordings. Yeah, so we have a lecture on each of the 4 homeworks. And as I think you already know, as Giovanni explained yesterday, you're supposed to do 3 out of 4 homeworks. So you should pick your 3 favorite ones out of the 4. And then sometime after Easter, there is an opening to sign up for separate sessions for presenting your homework. So that's done individually. I think you're allotted 10 minutes each, and we will examine the presentations. But we will get more information about that or reading Canvas. What else did I want to say? Yes, on Friday there is a lecture like this in the morning where Christian will talk about deep reinforcement learning. But then at 10 to 12, there's also a help session on the homeworks. So if you start looking already now, you can get some advice on basically, I think, how to get started on the homeworks. I mean, you should read through and come with questions. So that might be a good time to start thinking about which 3 homeworks you want to do. Yeah, and I think that's all I had to say now. So let me get started with the presentation. So I'll try to do a little bit of a hybrid presentation here. So I've prepared some slides, but which is actually just mostly placeholders. I've put in images that I want to use, and then I'll sort of take live lecture notes here. So graph neural networks. They are an upcoming form of neural networks, also known as message passing neural networks. So the basic idea is, and I will explain this in more detail, but the basic thing is to take sort of the concepts from, we know about convolutional neural networks, that they are very proficient when used for regular data on grids. So for classifying images, etc. But what if the data is of the type which is not as regular? So maybe the data is better put on a graph. So one example here that I'm showing here is a recent application using graph neural networks for antibiotic discovery. Yeah, and that's one of the, I think, most promising venues for using graph neural networks, is to look at chemistry. So yeah, writing or presenting a molecule as a graph is quite natural, and we will get to that in the next slide, actually. So the outline of this presentation is, I will tell you briefly what is a graph, how do we describe it, what types of tasks might we want to use graph neural networks for. Yeah, I will tell you something about the difference between a graph neural network and a convolutional neural network. Show you some example of graph neural network layers. So convolutional neural networks are more or less, I mean, they come in one flavor, but graph neural networks, you can formulate many different types of convolutional-like layers. Then finally, I will also tell you briefly about the homework. Now, I would strongly urge you to look at YouTube videos that I've posted on Canvas. Especially the first one, I think, is a very nice and sort of more in-depth discussion about graph neural networks. Okay, so moving on. What is a graph then? Well, so here is an example of a simple molecule with 3 different types of atoms and the structure. And of course, the thing to the right is the graph representation of that molecule. So a graph is a collection of nodes and edges. Yeah, so I see I have a question, I'll get to that. So let's say we have an index I that runs from 1 to a number n. So we have n nodes. So yeah, the nodes are here, and the edges are then a collection of objects specifying I to j. Yeah, so here we have, I think this is pretty obvious, but these are nodes and these are edges. And maybe we want to enumerate these, or let me call them 1, 2, 3, 4, 5, 6. So here I have n equals to 6. Yeah, so I have a question here about on the chat about the first YouTube video. How deep one should go into the maths? No, you don't have to. I know it was got a little bit technical after a while, and you don't have to dig into all of that. Certainly not. Right, so that's the basic structure of the graph. Of course, we want to have a little bit more mathematical description of the structure or the connectivity. As we see, there are not edges between all the nodes, right? And so the structure is given by the adjacency matrix. Aij. Yeah, so that's an n by n matrix. So Aij is equal to 1 if there is a node from I, if there is an edge from I to j. Aij is equal to 0 if no edge. Yeah, and actually in this lecture and in the homework problems, and I think, yeah, we will only consider undirected graphs. Meaning that Aj is equal to Aij. So if we take this graph now as an example, we can actually write down A, right, or at least some of the entries here. So if I start with the first node number 1, that's connected only to 4. So it's like 0, 0, 1, 0, 0. And the second node is connected to the 4th as well. Yeah, and where's this? Yeah, and that's similarly for the third one, right? Whereas the 4th is connected to the 1st, 2nd, and 3rd, and the 5th actually. Yeah, now that I've done almost the whole matrix, and then the 5th one is connected to the 4th. If we write this out, maybe it was not my most brilliant plan to write out the whole matrix, but let's see. I think it should go like that, and it's symmetric, right, for an undirected graph. Yeah, so that describes the structure of the graph, the nodes and how they are connected with edges. But of course, to actually do machine learning on this, we probably want to use more information, and there hopefully is more information that we can use about the graph. Structure. Yeah, so in the example here, we see that there are different colors for the atoms. So that we probably want to take into account somehow, that these colors, of course, indicate that these are different atoms. And there may also be information about how sort of the equilibrium distance between the atoms in the molecule, which we can encode in information on the edges. So the way this is typically set up is that you have some feature vectors on nodes and edges. So sort of, yeah, there is a vector sitting here on each node. We can call this, let's see, did I manage to get the same order here? 1, 2, 3. Yeah, so these feature vectors are called, I will call them xi, and on the edges I will call them eij. So there is some vector living on the node, and there is some other vector possibly living on the edges, living on the edge. And yeah, so for example, I don't know actually what the information was given for these molecules, but in the simplest case, maybe these vectors are not really vectors, but just scalars. So E45 could be the distance, Euclidean distance, 4 to 5. So then it's not it's a scalar, not vector, right? But that's of course not a problem. We can deal with that in the same sort of set framework. And X3, let's say, maybe it's just the label of the type of molecule. But there could be lots of more information. So another example of this, which is actually one of the data sets you will look at in the homework problem. It's the Quora data set, which is nicely represented here. That actually is a citation network over papers. So an edge here means that one paper cites another paper. And the papers then are nodes. And there are, in this data set, 2,708 nodes. And here, each node or paper actually has a 1433 dimensional vector, feature vector. Which corresponds to what's called a bag of words, so of some keywords. So you have a bunch of keywords and you see if those exist in that paper, and those are mapped to this vector. And there are 7 classes of papers here. And so we will get back to that, but one can imagine also wanting to do different types of learning tasks here. So in the Quora example, we will actually look at what's known as node classification. So you have the, the classes of some of these nodes, and you want to predict how is that other papers categorized? What are their labels? Yeah, so I think I'll move on there. So yeah, so I just started getting into this topic of what sort of things do we want to do on graphs. So I think the first example here that we already looked at would be what's called graph classification. Classification. Yeah, so basically here, does this molecule represented as a graph have antibiotic properties or not? So is the graph in class 0 or class 1? So typically, the type of training data you would have here, or what you would look at is many graphs, right? You would look at lots of different graphs, some of them labeled, and you learn from those to predict the labels of other graphs. So that's one thing you may want to use graph neural networks for. Another thing that I already mentioned then is node classification. So, as I said, is the paper in class A, B, C, etc. And for this example, you will typically just have a single graph that you deal with. So whatever you learn on this graph may not generalize to another problem, another type of graph. Because things you learn on this graph is probably particular to this graph, whereas in the first example, you want to learn something which is general for this type of graph. A third example is what's known as link prediction. Sorry. And so here's an image from representing a social network. So there you might want to know, as already seen in this picture, whether or not there is a connection, a link or an edge between a person or node 3 and 5, perhaps. Yeah. So those are.
Can I ask you a question about that last one?
Mm-hmm. Yeah.
So is that essentially that you would train such a network on graphs where you already have all the edges, and then you present the case where you don't have any edges, and you pretty much ask it to fill in the edges, or?
Yeah. So there, I think you would typically have several graphs to train on, or perhaps you use subsets of the same graph. But not necessarily. I mean, it could be that you also have information on the nodes, and so actually from the information on the nodes related to where you have edges already, you might be able to learn from that whether or not there should be edges, depending on, you know, if 3 and 5 have similar node information and similar connectivity to other edges, then maybe there should also be an edge between 3 and 5, or vice versa.
Okay, so you could feed it sort of an incomplete graph.
Yeah.
Okay.
Yeah. So a question here, is that used for friend suggestions in social networks? If graph neural network, I don't know. That's a good question, Luis. I don't have the answer to that. Another question on the Quora data set. It's extensive. Is there an equivalent batch size for graph neural network to split the data during? Yeah, I don't think, let's not get into all the details. The Quora data set is not that big, so I don't think you will have a problem. That's just a single graph. So I don't think there is a problem with the training based on that, but we can discuss that when we have the homework session. Yeah, so now I get a question on, I wonder if someone already read my lecture notes, but I don't think that's possible. So there's a question on semi-supervised rather than supervised learning, and I was just going to get to that actually. So that's my next slide here. Yeah, so one of the, let's say, hallmarks of graph learning on graphs is that one can actually, it's quite natural to look at semi-supervised learning. Of course, supervised learning, you've seen a lot of that in probably earlier neural networks in the first neural network course. So if I start with that, just to remind ourselves, then of course you have a labeled data set. Yeah, and you just use those labeled examples to train. So let's say, I would say graph classification is typically of that kind. I don't know if it always has to be, but supervised learning. So, yeah, so you have a set of labeled graphs, just like you would have a set of labeled images for image recognition. And you use those for training. Yeah, I don't think I have to get into more details on that. Now, so what is the semi-supervised learning? So before trying to explain a little bit how it works on graph, I think this example that I actually found, this image on Wikipedia, is a nice representation of what semi-supervised learning is. So here we have two labeled data points. And many unlabeled. Now, of course, if we use some sort of clustering algorithm, and perhaps this is a nonlinear kernel method, a nonlinear support vector machine, which try to separate these into two data, into two clusters. And then, of course, given the two labeled ones, we can actually learn a good classifier by just trying to distinguish these into two data sets. So then we use, or two clusters. So then we use also the unlabeled data points for the learning algorithm. So that's what we mean with semi-supervised learning. So we use clustering, extract info from unlabeled. Yeah, so node prediction would typically be of that type then. So that's what we will do for the Quora data set. Yeah, so as an example, so in the Quora data set, I think we have 140 labeled nodes out of how many is it now? Out of 2,708. So that's not very much label data if we want to predict all the nodes. So I guess one could, and actually that's the first step in the homework problem, is to actually try to just do supervised learning on this. So given the feature vectors, these 1400 dimensional vectors. You can, of course, train a simple multi-level perceptron with this vector as input and the label as output. But given this very limited training set of 140, you're not going to be able to do very good at training a classifier like that. So then instead we can also take advantage of the fact that we have connectivity, we have information about the connectivity, how these papers are related. Yeah, so then we use info about how papers are related. So the citation graph. So building that information into the pipeline, we can get a lot better results. I mean, it's not completely obvious. I don't think I will get into much more detail, but actually how this is set up. So the type of network layer, and I will discuss that shortly, a couple of different types, but it may depend on what type of graph you have. Yeah, so actually, yeah, so one example which is also discussed in this YouTube video, which I think was quite important, is what they call a Homophilus graph. And that's the case where adjacent nodes are more likely to share properties. And then, of course, if that's the case, it's quite natural it's easy to understand that, okay, if I know something about one node and I have an adjacent node, then it's more likely than not that this also has the same label. So it's quite easy to see how one can transfer that information between nodes. Yeah, and finally, one can also actually use graph neural networks for unsupervised learning, in the sense that there is already some structure built into the graph neural network that even without training, it does some processing. Of course, you can do much better with training, but the GNNs even not to train. And there is a, yeah. Okay, so let's see. I guess we should, yeah, let's go on, and then we take a break at a 1:45, I think. Yeah, so now I sort of, let's see. So I have discussed the type of tasks we want to do and different types of learning schemes on graphs. So now let's sort of get down to business and actually discuss how to construct neural networks on graphs. So then we want to think about convolutions on graphs. So here's the CNN, the standard CNN filter. And this would be what we might want to think about as a convolutional structure for graph neural networks, so GNN filter. Yeah, so of course, standard CNNs. So they work on grids, so regular structures. Yeah, so in particular, each point here has a fixed number of neighbors. So I mean, we could think of the grid as a graph also, if we like, but then it's a very regular graph. So each node, if I think of this one as a node here, has fixed number of neighbors. Yeah, and of course, let's see. I don't know if I should. Yeah, so let me try to draw a little. Let's say I have an image here, and maybe I have 3 channels. This is the input, 3 channels. And then of course we have these filters here. Actually, the point I wanted to make here is that, of course, we have the filter has, CNN filter has weights to all pixels, different weights, right? So let's say a 3x3 filter has 9 trainable weights. Plus a bias, possibly. But how do we actually set up a similar thing on a graph, if we want to start thinking about that? So I guess, I mean, clearly, I think we want to use the adjacency matrix. I mean, that's the structure of our graph corresponding to the structure of the grid for the image. So we want to use adjacency matrix that defines our neighbors in this case. So that might seem pretty straightforward, sort of replacing, just making the filter based on the adjacency matrix. The problem, though, why this is not so easy, is that we actually don't have a fixed number of adjacent nodes. So how many weights should we have? Yeah, so I mean, if we look at this one, we cannot really, at least in a very simple way, say that we have 5 weights to this filter, because of course, if we look at another neighbor, that will have a different, if you look at another node, that will have a different number of neighbors. And yeah, how do we actually train that using a filter where the number of weights has to vary? So typically in the simplest case, we actually assume that we have the same weight to all neighbors. Yeah, so let me, I think before the break, we start going through the most basic and standard form of a graph convolution. which is from this paper, Semi-Supervised Classification with Graph Convolutional Networks, Kipf and Welling. Yeah, so to explain how that works, I mean, it's actually quite straightforward and sort of a natural way to formulate this, I think, but let's go through it step by step. So first of all, we look at the adjacency matrix and we add self loops to that. So I'll work with this object called A tilde, which is A plus 1. So it's just saying that, okay, we have a graph here. And we sort of just add edges that go back to the node itself. Yeah, so A tilde in this case, we just have ones on the diagonal. Let's say this is 8, 1, 2, 3. Yeah, would be something like this. And we also want to use its degree matrix. So it's a diagonal matrix where on the diagonal it's the degree, including the self loops. So the number of edges simply going into and out of that node. So this thing, the I tilde, is equal to sum over j aij. So it's just counting the number of ones here. And let me also call that d tilde I. The tilde here is because normally when you count the degree of a node, you wouldn't count the node itself. And all the off-diagonal entries here are 0. And now, maybe that's the last thing I say before we take a break here. And that goes for all of these convolutional type layers, is that they take a graph to an isomorphic graph. So it takes a graph to a graph with the same structure. Graph to isomorphic. Same structure. That is, we have the same adjacency matrix. But we get new node features. So in this case, I will not think about edge features, but only consider node features. So what it does, it gives new node features, that the thing it transforms. xi is mapped to xi prime, which then may have a different dimension. So let's see if this is dimension d, then this may be dimension d prime, which may be smaller or larger. And we will see that actually this transformation is very similar to just a simple single dense layer transforming this vector, and then you sort of aggregate over the neighboring nodes. But I think we should take a break there and continue after the break. So let's start again at 9. I'll pause the recording. Okay. Let me start the... Okay, let's get back to business. Yeah, so we were sort of in the middle of the discussion of this basic graph convolution. And so I was saying that, yes, this will not affect the adjacency matrix, so we still will have the same graph. And that goes for all of these types of convolutional layers. We will, in the next 2 or something slides, look at pooling layers where you actually change the structure of the graph, because you might need that as well. But now sticking to this, then what happens is that you make a transformation on the node feature vectors. So one way to formulate this now is if we can first of all put these vectors in a graph, in a matrix form. So let's do that. Feature. Yeah, so we simply make this object which I call X, which is just a matrix where I put the vectors in the rows here. So I put X1 here, X2, X3, etc. So that will be a n by d dimensional matrix. And then this layer does the following. It outputs feature matrix X prime. So let me write it down and I'll try to explain what actually happens here. So it looks like this. I take the square root of this degree matrix. Of course, that's not a problem because it's a diagonal matrix. So you just take the square root of the diagonal entries. And then X times W. So what are the things that go in here? Yeah, so the sigma here is a general way of writing a nonlinearity.
Sorry, quick question there.
Sorry?
Is it minus 1/2 for both the one before and the one after?
Minus a half, yes.
So that's 1 over the square root.
Yes, absolutely. Yes, it's 1 over the square root. Yes.
Okay, because is it the same before and after, or is it supposed to be like an inverse one of them?
It is the same before and after, because A tilde is not a diagonal matrix, it actually matters. Yeah, it doesn't commute, so it actually makes a difference if it's before or after.
Okay, thank you.
Yeah, but I will actually write it out I think in a simpler format shortly. But let's look at this form first. Yeah, so that's a non-linearity. That's like a ReLU or a tanh or something. And so what do we have here? So yeah, so here we have X. This is our input, which is n by d dimensional. And the W now is the weight matrix. That's the one you train. That has trainable weights. That will have dimension d by d prime. So you see what it actually does is quite simple. It takes all of these node feature vectors and just transform them to a dimension d prime. It's just a linear transformation into a dimension d prime vector. And it's the same weights to all the nodes. So that's just like, as I said before, just like a single dense layer. It does exactly the same thing. Of course, before you act with the activation function on it. Yeah, but then we also have this thing in front. So that is actually an n by n. That's simply an n by n matrix, right? So the output here will be n by d prime. So that's how you get your, yeah, the rows here will just be the new feature vectors. Yeah, so it actually has the same, so that's important, same weight matrix. Same weights on all nodes. So that's, I guess, a very simple way to solve this problem, that you have varying number of neighbors, as we said before. Yeah, so what is actually going on here? Well, you see, you multiply by the adjacency matrix. This d tilde, they just normalize it, renormalize the weights. But basically, it just collects, it just aggregates the feature vectors from all the adjacent nodes. That's basically what this layer does. Yeah, so actually a simpler way to write this, which I think is more obvious, is to actually write it out feature vector for feature vector. So then we can actually write equivalently. We can write xi prime is equal to sigma sum on j a tilde ij. So that's just 0 or 1, depending on whether there is an edge or not. You see now a sum over j here, divided by square root of d tilde I, d tilde j. So that's why actually you needed 1d on one side and 1 on the other, because then you actually get these, you normalize with the degree of both of the incoming and the node that you're looking at. It's like that. And yeah, if we want to act on a single vector here now, we actually need to take the transpose of this weight matrix xj. So I think that's a little bit easier way to see this. So you basically just transform all the vectors, transform as a linear to d prime dimensional vector with your trainable weights, and then you just collect add up from the adjacent neighbors. Yeah, so as I said, maybe I'll write this as well. This is just like a single dense neural network layer. Yeah, and the reason for having this 1 over the square root of d times d is just to normalize, so that if you have nodes that are highly connected, that their feature vectors don't become very large in comparison. yeah, so what it does, in summary, collects information isotropically from neighbors. And yeah, if one thinks of it, it's sort of a one hop per layer. So if we have one of these layers, one layer gathers information from adjacent nodes. And then if we have another layer of this type, effectively what we have done is we have collected information into one node from nearest and next nearest neighbors on the graph. So there is actually a sort of a warning here. I want to pose is that if you have too many of these types of layers, because the structure is sort of simple, so if you have too many layers, you may smear out the information. I can imagine you're just spreading out the information among all the nodes, and eventually you might sort of get the same information content in every node, and then you've sort of lost the point of having a graph. So that's something you may notice when you play around with this a little bit, that it's not, you may not get better results by just adding more layers. It may in fact get worse. Okay, so one thing we noticed in this simple structure, and as I said before, there is no edge information used except for the connectivity. It could be that I didn't have any edge information, but if I do, I probably want to use it. So just mention a simple variation on this. If we just have an edge, like a scalar feature vector, or yeah, scalar edge weight. So it's a scalar edge feature. Yeah, since we collect information from the neighbors, it's quite natural to just simply build that in. So we could have something like this. Xi prime is equal to, and here I'm not even going to try to normalize it. So then I might have one weight vector that acts on the node itself, and I add up with another weight vector the feature vectors from the adjacent nodes. Yeah, and here I've assumed that Eij is, if Aij is 0, then Eij is obviously also 0. So it does something similar to the earlier structure, but it just weighs the different edges. So heavy edges. Wait. Yeah, and of course that's just a very simple variation on the theme. Now let's look at something a little bit more complicated. So one thing about the structure we looked at before is that it's what's called an isotropic layer. So it just adds up in the same way, aggregates over all the neighbors without taking into consideration that those neighbors may be different somehow. So a way to do something more fancy is to look at what's called graph attention networks, graph attention layers. So as I said, the basic layer is isotropic. All adjacent nodes. Oh, may I have missed the question here? Yeah, I guess that was a question on this previous thing here. If you normalize, yeah, yeah, I think you're right that if I would normalize, well, I suppose I still could normalize with respect to the number of adjacent nodes. They will still be weighed differently. So I think one could think of doing both, even adding a normalization depending similarly to the previous one. But I think there are actually, whether or not it's useful to do this normalization, I think has been discussed in various papers. One it might even be better not to have this normalization depending on the problem at hand. Okay, so anyway, yes, so I was saying here that all adjacent nodes are treated the same. Of course, that was sort of modified if we actually include edge weights, but if I look at I think now I have a problem again where I don't really have any edge weights. So all the information is in the adjacency matrix and in the node features. And then we may want to be more selective. Yeah, and of course this graph or this in general attention mechanism has of course been very successful. So basically being selective about how you value the information, and in the graph context it will be basically selectively picking out what neighboring nodes you want to extract information from primarily. So let me explain then. It's pretty straightforward how this works, I think. So attention gives selective feedback from adjacent nodes. So we just write it up similar to what we did before. So xi prime is some nonlinearity. We sum over the other nodes, j. And now we have some coefficient alpha ij. And we have a weight times xj. So again, now I put the W in front here, so that will have, well, I guess I did that before as well. So that will be a D prime by D matrix, weight matrix. If this thing is D, just to remind ourselves, this thing has dimension D prime. And now of course, the important thing is here, these alphas. These are what's known as attention coefficients. So those will obviously tell you how much of node J to add onto node I. How much of the feature vector node J to add onto the feature vector node I. So those we also set up and train to extract those. So the way we formulate this is that we say that alpha ij is a softmax over something I'll call it epsilon ij. And the reason to have the softmax here is just to normalize it, basically. So the sum over all the neighboring nodes j will add up to 1 in this case. So I write that this is just to spell out, to make clear what the softmax means here, is that we sum over the neighboring nodes. So it's a sum over k e to the epsilon I k. And now so what is this epsilon then? I think it's typically written as an e, but I didn't want to use e not to confuse it with the edge weights that I used before. I mean, in practice, this is sort of an effective edge weight, the alphas that we train to find the edge weight here. So the epsilon ij is now written like this. I can write this actually as a scalar product, a dot, and I use the same weight matrix here. And I'll explain what this object is. This is concatenation. So this is simply putting the two vectors on top of each other. There's basically, we have w times xi here, w times xj. And remember, this one was dimension d prime. These are the transformed feature vectors, and this is 2d prime, this whole object. And then, of course, this is then a trainable vector of dimension 2d prime. So this is the attention vector. And so the object we get out here is simply a scalar. And I multiply by the adjacency matrix here to make sure that I don't get any connections where I don't have any connections in my graph. That's attention vector, that's trainable. So this will, once we have trained that will look at the two neighboring nodes I and j and decide whether or not node j is important to node I. So in that way one can learn a pretty sophisticated way of taking into account the neighboring nodes. And in fact, one can also have, which is often a good idea, to have multiple, what's called attention heads. That may look at different properties on the neighbors. So you would have like a weight wk and attention vector ak, where this k goes from 1 to some capital K, so multiple of these. And then your output in this case, xi prime, would then be actually a concatenation of these. So sum on k xi prime. Yeah, now I have a lot of indices here. Yeah, so basically just for each of these heads, you get one d prime size vector, and then you just add these on top, and this is your new feature vector. Okay. Yeah, I think I'll leave it at that and actually move on here. Notice that I'm actually running a little bit short of time here. I just have a couple of slides actually, so I guess we will finish in time. But I want to also get to, so these were examples of, I would say, convolutional layers. The main point being that they actually don't change the structure. But of course, we may need to change the structure of the graph. And in particular, if we want to do a graph classification, it's hard to see how we would do that on the full graph with all these feature vectors sitting on each node. We need to get that together into one piece of information somehow. And so for that, we would use pooling layers. So yeah, just to recap here. So convolutional layers, they give graph to same graph, basically. Just new features, right? But so then the question is, how do we get output for graph classification, for example? We want to put a single label on the graph. So yeah, single. And we actually may more generally want to decrease or unify the graph size. If we have data sets with different types of graphs, we may want to get them into the same structure. Or decrease the size of the graph systematically. Yeah, and so for this we would use pooling layers. So basically they just pool nodes together. And of course, for some types of objectives, you may not want to do that. So if you do node classification, then you typically, well, you would not want to use a pooling layer. If you do node classifications, you do want to have the full resolution of the graph and look at the individual nodes, and maybe use just a dense layer on the feature vector of each node to output the label on that node. But for other tasks, you may want to do this. So one simple way of doing it is what's called a global pooling. So that actually corresponds to taking the graph and producing a single vector. So actually reducing the graph to one node. Like that. Yeah, and one way, most simple way to do that is just to do a global mean pool. Yeah, which is just adding up all the feature vectors over all the nodes. So that's something which is quite natural to do if you want to do graph classification. So we just add up all the feature vectors and then do some additional, perhaps have a multi-layer perceptron that, so it's dense, several dense layers acting on this maybe. Yes, I had in mind also representing something a little bit more fancy here. Maybe I'll, let's see. Yeah, I think I have 15 minutes left. I can probably briefly describe this as well, because it seems like a quite interesting layer. So this is another example then of a pooling layer, which is also based on the attention mechanism. So basically what we want to do here is select the k most. It could be a fraction, but I'll think of it as a certain number. So we want to select the k most important nodes. Yeah, so we would start out with the n nodes and eventually end up with k nodes. Oops. K less than n. Yeah, so then we can set this up using self-attention. So it's basically what we did before, but we want to output now a scalar value for each node. And the way it's formulated in this paper is basically using this most basic form of a graph convolutional layer. So if you remember, formulated like this. The only difference is now that I have a vector here instead of a weight matrix. And I do this normalization here, d twiddle I, d twiddle j. And so A is an attention vector in this case. So if this had dimension d, this will also have dimension d, so that the output here now is a scalar value. And then I simply keep k nodes with highest z value. So in practice, I'll just mask out. So if that's not supposed to be a vector. If I look at the adjacency matrix, I simply remove the nodes that I don't want. No. So basically Aij goes to some A, sort of write this a little bit informally as a mask on Ij. And so if this is n by n, this is now k by k. It's just removing the rows and columns of the nodes that I have now decided I'm not going to keep. And actually, what they have, at least in this paper, I'm not sure how useful that is, but they also actually renormalize the feature vectors according to this weight. So that the more important the nodes are, the more you blow up the size or the magnitude of their feature vectors. Yeah, so that was one final example of a type of structure And there are, of course, lots and lots more. And so I think what I wanted to say here, and yeah, the final message here, and which will be relevant then for your homework, is you basically put together convolutional layers, pooling layers, depending on the task. Sort of yeah, and I guess the message again, which I noticed from playing around a little bit with this, is that you need to be a little bit aware of overdoing. So constructing too deep networks may not help you here, which I think, I mean, if you compare to a normal convolutional network, typically if you make it very deep, okay, you may run into the risk of overfitting, but you would typically not lose performance as long as you stop early. But here that really happens, I noticed. Okay, so then finally, actually, so I have 7-8 more minutes, and this is my final slide. So I want to say something about the homework then. I was thinking I would give a quick walkthrough, but actually most of the stuff there is really what I've been talking about here. But I just want to also point out that the recommended library for working with these graph neural network, at least for this homework, is PyTorch Geometric, because that's what we've used. So we know that it works for that. And there are also some example notebooks actually here, Colab notebooks that will get you started on the homework. But maybe, let's see if I can switch to. Share this instead. I think you see the homework now. Yeah, so there's some background here, which is basically maybe not as in-depth, but basically what I've discussed today. And then the first assignment is on the Quora data set, which I also described briefly. Yeah, and as I just mentioned, PyTorch Geometric, I think, is the way to go. You're welcome to use one of the other libraries, but then you could maybe expect a little bit less help from me and David, who have used PyTorch Geometric. Yeah, so there is that. Yeah, so the problems then, so you basically, we have two assignments on the Quora data set. The first part of this is really, yeah, basically setting up this using the standard basic convolutional layer. And actually, first of all, trying to train it just with a single dense layer. It's quite nice to see that that doesn't really work that well. Maybe I'm not going to go through in much more detail here. Yeah, and then try to use more sophisticated, maybe graph attention layers to get higher performance on this Quora data set. It actually turns out that it's not so easy to do much better. There is some data. There is actually benchmarking, one place where they've collected all the classifications, how successful people have been in other papers, and you're certainly not going to be able to outperform that, and probably not get close. But the point of this is try it out, use different layers, and then of course during the examination you should show us your code, or not dig into the details of the code, but you should describe how things work and explain to us. Yeah, so that was the first data set. And then there's also a sort of more experimental data set, which is based on some work that I'm doing in my research, which is in quantum error correction. So it's a graph data set which is based on what's called the surface code. So it's a error correcting code. And you certainly do not need to read up on the background here, but it's served to you as a data file. So you can just upload that into PyTorch geometric, and try to, so that's a graph classification task on this data set. Then it's 4 different classes. Yeah, but if when you start looking at this and if you have questions, we have these sessions to discuss that in more detail. So I think I'll just stop there actually, and leave a few minutes for questions if there are any.
I have a quick question on the attention coefficients, or what we call them, the alphas. So do they essentially replace the adjacency matrix in terms of having a representation of the graph?
Yes, they do in the convolution, or in that layer. So for the output, the feature vectors in the next layer, but you don't really change the adjacency matrix. That's still there.
Okay.
Yeah.
But they are still 0 when there's no edge, right?
Yeah, I think that one can actually do that differently, but I think that's the standard way of doing it, as I also showed in my notes, that you actually, in those attention coefficients, you actually build in the adjacency matrix. Well, I think I mean, if you don't do that, then you sort of basically leave out the graph structure, which is what you don't want to. Yeah, you probably don't want to do that.
And then I didn't really understand. You stacked the the weight multiplied weight matrix multiplied by the features. You stacked them on top of each other. Was there any particular reason for doing so? You wanted the attention vector to be of dimension 2d prime. Was there any particular reason?
Here?
Yeah, exactly.
Well, you want to obviously somehow get the information. I mean, this, for the attention coefficient, you want to get the information from both of these nodes, node I and node J on the graph. So somehow you need to get both of their feature vectors into this expression. And so then I think it's just a natural way, maybe the simplest way, to just get both of these vectors into the equation. It's just,
is that a J on the right hand side there, on the index?
Sorry?
Is that a J on the index on the?
Yes, that's a J. Yes.
Oh,
Epsilon
okay.
ij. Yeah, and it takes so this is the transformed feature vector of node I, and that's of node J.
Okay,
and
that
that's
makes a lot.
You collapse
lot
against this attention vector to decide, how important this edge is. Yeah, and as you can see here, I also have the A tilde explicitly taken into account here, but I think that's not always the case. But I think that makes sense.
Okay,
And
thank you a
that's
lot.
actually what they did in this paper as well. They only have attention coefficients where there are actually edges in the original graph. Okay, I think it's time to